Hi everyone, my name is A.Freinberger and I'm from Austria.
My name is A.Erbasan and I'm from Turkey.
And together we are going to present our Praise Summer of HPC project, Fusion Reactor Materials, Computational Modeling of Atomic Scale Damage in Irradiated Metal, which we carried out at the Barcelona Supercomputing Center.
The main goal of this computational study is simulating the effect of irradiation damage on thermal conductivity of tungsten. Let's get started with nuclear fission.
Nuclear fusion is the process that makes our sun and the stars shine. Realizing nuclear fusion here on Earth could be the key to a safe, sustainable and carbon-free energy source. The most promising reaction is the fusion of deuterium and tritium, two isotopes of hydrogen, as illustrated on the right. This process takes place in a plasma state under immense heat and produces a high-energy helium nucleus as well as a high-energy neutron. Needless to say, materials inside a fusion reactor have to withstand high temperatures and radiation doses. A candidate material for so-called plasma-facing components in a fusion reactor is tungsten, due to its high melting point and its very good thermal conductivity, both of which is crucial to dissipate the high amounts of heat efficiently and prevent component failure. It is the thermal conductivity that we were focusing on this summer, especially considering damaged tungsten systems.
In this work, we are using molecular dynamics, which is a computational method for simulating movements and thermodynamical properties of atoms and molecules. In molecular dynamics, the interacting pieces are atoms and they are modeled as point particles. The interaction of the atoms is described with interatomic potentials, and once we have the potentials, we can calculate the force on each particle and predict the time evolution based on Newton's second law. The interatomic potentials can be described by several methods. We use embedded atom model potential, which is specifically designed for metallic systems. And finally, we use free and open source code LAMPS for molecular dynamic simulations.
Since we are interested in the thermal conductivity of irradiated tungsten, we use an algorithm called creation relaxation algorithm, CRA for short, to simulate radiation damage inside the metal at relatively low computational cost. In its essence, this method first displaces a random atom in the crystal to a new random position and then minimizes the energy of the new configuration, thus introducing pairs of vacancies and interstitial atoms, also called Frankel pairs. This procedure is repeated until the desired level of damage is reached, as measured by the amount of displaced atoms. As will be explained shortly, we simulate our systems at specific temperatures using a heating procedure, which leads to a recombination of some of these vacancy interstitial pairs. Thus, the initial number of defects before the heating differs from the final number of defects after the heating.
In order to calculate the thermal conductivity of damaged tungsten, we first create our simulation box with 2.5 million of tungsten atoms. Then, using CRA method, we introduce damage to the 10% of the atoms in the center of the simulation box. And before we proceed, we heat up the system to a desired temperature using statistical thermodynamic ensembles. And once we have a system at a certain temperature, we introduce a heat source and a heat sink located at the lower and the upper quarters of the simulation box. This is achieved by withdrawing kinetic energy from the heat sink and supplying it to the heat source. In the illustration below, you can see our simulation box, which is lying on the x-axis. And in the middle, we have the damage part. Heat source and heat sink are represented with red and blue colors. The resulting heat flux leads to a steady state temperature gradient, and from Fourier's law we obtain the thermal conductivity kappa. As you can interpret, the simulation box is huge and one could expect that simulations can take lots of time. Thanks to the parallel programming and facilities at Barcelona Supercomputing Center, it is enough to run the calculations in approximately 500 computer cores for 2 or 3 hours.
The following two plots display the temperature profile of an undamaged system on the left and a damaged system with 1038 final defects after recombination on the right, both at a temperature of 300 Kelvin. The temperature profile was computed along the major axis of the system in the direction of the imposed heat flux. The interesting part for us is located in the middle, which corresponds to the middle 10% of the system as described on the previous slide. In the undamaged region, we observe a smooth temperature gradient from the hot to the cold region. In contrast, in the damaged system, a clear change in the slope of the temperature gradient can be seen. This indicates poorer thermal conductivity. The perfect system exhibits a thermal conductivity of 18.59 watts per meter Kelvin, while the damaged system has a thermal conductivity of only 10.7 watts per meter Kelvin. To better quantify this behavior, we analyze the trend in thermal conductivity with respect to the overall damage of the system as measured by the final number of defects. As can be seen, an increase in the number of defects comes with a decrease in thermal conductivity. We also observed some deviations from the main trend, possibly due to the statistical nature of the simulations. Next, we advanced the simulation to 600 degrees Kelvin.
We have calculated the thermal conductivity of tungsten at 600 Kelvin for several different damage levels and plot the results as a function of number of defects after recombination. The first thing that can be interpreted from the results is that the thermal conductivity is lower compared to the 300 Kelvin case. Further, since both CRA method and thermal equilibration process include randomness, we cannot predict the type what kind of defect will be formed after simulations. Therefore, to reach a conclusion about what kind of defect affect the thermal conductivity the most, we need further studies, and they can help us to understand the physics behind the damage level versus thermal conductivity.
In summary, we can say that thermal conductivity of tungsten metal clearly decreases after radiation damage. Likewise, we observed a decrease in thermal conductivity with higher temperatures. In order to counteract statistical fluctuations and to be able to make more definitive statements, an average over several simulation results would have to be calculated. Future studies of great interest could include simulations at higher temperatures. The animation on the right shows an example for the evolution of defects as observed in the simulations. Red are interstitial atoms, forming extended defect clusters, and blue are vacancies. The green lines indicate dislocation loops, a special type of defect structure. Finally, we would like to thank our supervisors, Mary Kate Jesse and Julio Gutierrez Moreno, for their active support, motivation, and their non-stop availability. Also, we would like to thank Mervi Joanna Manzinen for having us in the PSC Fusion group and giving us this opportunity. And of course, thank you to the Praise HPC program for this nice experience.